Welcome to Chemistry, Corrosion and Cathodic Protection. In this presentation, we explore the electrochemistry of metallic corrosion, the destructive attack of metal by its environment, and the engineered countermeasure of cathodic protection. We begin with the fundamental oxidation-reduction reactions that drive rust formation. Then we examine the thermodynamics and kinetics governing corrosion rates. Finally, we master how sacrificial anodes and impressed current systems protect steel structures from the seafloor to the tundra. 5 quiz questions and 5 fully worked problems reinforce all concepts. Corrosion is the spontaneous deterioration of a material, usually a metal, because of a reaction with its environment. The most familiar example is rusting of iron. Iron reacts with oxygen and water to form hydrated iron oxide, also known as rust. Corrosion is an electrochemical process requiring an anode, a cathode, an electrolyte, and an electrical connection between them. The global cost of corrosion exceeds $3.1 trillion annually, roughly 3.4% of world GDP. Understanding the chemistry lets us predict, prevent, and control it. Corrosion takes many forms depending on the metal, environment, and mechanical conditions. Uniform corrosion attacks the entire surface evenly. It is the easiest to predict and allow for. Galvanic corrosion occurs when two dissimilar metals are in electrical contact in an electrolyte. Pitting is a localized attack that forms small cavities. It is insidious because the damage can be severe with little visible metal loss. Crevice corrosion happens in confined spaces where oxygen is depleted. Stress corrosion cracking combines tensile stress and a corrosive environment, leading to brittle failure. Corrosion is fundamentally a redox process. At the anodic site, iron metal oxidizes, releasing electrons. Fe gives Fe2++ 2 electrons. At the cathodic site, electrons reduce oxygen in neutral or basic water. O2 plus 2H2O plus 4 electrons gives 4OH-. In acidic environments, the cathodic reaction is hydrogen evolution. Electrons flow through the metal from anode to cathode. Ions carry charge through the electrolyte. The corrosion rate is controlled by the slowest step, often the cathodic oxygen reduction. The driving force for corrosion is the Gibbs free energy change. A negative delta G means the reaction is spontaneous. The Nernst equation relates the electrochemical potential to concentration. The corrosion potential E-core lies between the equilibrium potentials of the anodic and cathodic half reactions. Pourbaix diagrams map the regions of thermodynamic stability. These regions are immunity, where the metal is stable, passivation, where a protective oxide film forms, and corrosion, where the metal dissolves. For iron and water, the corrosion region covers most acidic and neutral pH at moderate potentials. Thermodynamics tells us whether corrosion can happen. Kinetics tells us how fast. The corrosion current density I-car is directly proportional to the corrosion rate via Faraday's law. The Tafel equation relates overpotential to current. Eta equals beta times log of I over I0, where beta is the Tafel slope. A polarization diagram plots potential versus log current. The intersection of the anodic and cathodic Tafel lines gives E-core and I-core. The corrosion rate in millimeters per year is calculated from I-car using Faraday's constant, atomic mass, and density. Some metals spontaneously form a thin, dense, adherent oxide layer that isolates the metal from the environment. This is passivation. Stainless steel contains chromium, which forms chromium oxide, a self-healing passive film only 1 to 3 nanometers thick. Aluminum's aluminum oxide layer protects it from further oxidation, even though bulk aluminum is very reactive. Passivity can be destroyed by chloride ions, leading to pitting. The flayed potential is the threshold below which the passive film breaks down. Understanding passivation is essential for designing corrosion-resistant alloys. Cathodic protection is the most widely used electrochemical corrosion control method. The principle is simple. Supply electrons to the metal surface so that the anodic dissolution reaction, iron going to iron 2++2 electrons, is suppressed. When sufficient electrons reach the metal, its potential shifts negatively into the immunity region of the Pourbaix diagram. For complete protection, the potential must be lowered to at least negative 0.85 volts versus copper-copper sulfate in aerobic environments, or negative 0.95 volts in anaerobic conditions containing sulfate-reducing bacteria. Sacrificial anode cathodic protection connects the structure to a more reactive metal, the sacrificial anode. The anode has a more negative corrosion potential than the protected structure, so it becomes the anode and corrodes instead. Common sacrificial anode materials are magnesium for soil and fresh water, zinc for seawater, and aluminum alloys. The anode dissolves, supplying electrons to protect the steel. The current output depends on the potential difference and the circuit resistance. Anodes are consumed over time and must be replaced periodically. Impressed current cathodic protection uses an external DC power source, a rectifier, connected between an inert anode and the structure. The DC supply forces current through the electrolyte, polarizing the structure cathodically. Unlike sacrificial anodes, ICCP anodes do not dissolve. They are made from inert materials such as platinized titanium, mixed metal oxide, graphite, or high silicon cast iron. ICCP systems are used for large structures like buried pipelines, jetties, offshore platforms, ship hulls, and concrete reinforcement. The rectifier voltage and current are adjustable, allowing the protection level to be optimized over the design life. Cathodic protection is applied across every industry that uses steel in aggressive environments. Buried oil and gas pipelines are the most common application. Tens of thousands of kilometers are protected globally. Offshore platforms use both sacrificial and impressed current systems. Ship hulls and ballast tanks are protected to prevent corrosion in seawater. Reinforced concrete bridges are protected against chloride-induced corrosion from de-icing salts. Above-ground storage tank bottoms are protected from soil-side corrosion. Combined with protective coatings, cathodic protection is the gold standard. Coatings reduce current demand, while cathodic protection protects holidays and defects in the coating. Quiz question 1. Which metal would be the most effective sacrificial anode for protecting a steel pipeline? Option A, copper. Option B, tin. Option C, magnesium. Option D, silver. Take a moment to think. The correct answer is magnesium. Magnesium is the most active of the listed metals, with a standard potential of negative 2.37 volts. A good sacrificial anode must have a more negative corrosion potential than the protected metal. Copper, tin, and silver are all more noble than iron and would not protect it. They would actually accelerate corrosion if connected. Quiz question 2. In neutral aerated water, what is the dominant cathodic reaction in the corrosion of iron? Option A, 2H++ 2 electrons gives H2. Option B, iron gives iron 2++ 2 electrons. Option C, O2 plus 2H2O plus 4 electrons gives 4OH-. Option D, iron 2 plus gives iron 3 plus 1 electron. The correct answer is option C. In neutral aerated water at pH 7, the dominant cathodic reaction is oxygen reduction. H+ reduction is important only in acidic solutions. Option B is the anodic reaction. Option D is a secondary oxidation. Quiz question 3. Which material is commonly used as an inert anode in impressed current cathodic protection systems? Option A, magnesium. Option B, zinc. Option C, platinized titanium. Option D, cast iron. The correct answer is option C, platinized titanium. It is a common inert anode material for ICCP because it does not dissolve during operation. Magnesium and zinc are sacrificial anode materials. They corrode away. Cast iron would also corrode if used as an anode. Quiz question 4. Which type of corrosion is considered most dangerous because it is difficult to detect and can cause catastrophic failure? Option A, uniform corrosion. Option B, pitting corrosion. Option C, galvanic corrosion. Option D, erosion corrosion. The correct answer is option B, pitting corrosion. Pitting produces small pits that penetrate deep into the metal with very little material loss visible on the surface. The pits act as stress concentrators and can lead to sudden catastrophic failure with little warning. Uniform corrosion is easy to detect and plan for. Quiz question 5. What is the standard cathodic protection criterion for steel in aerobic environments? Option A, 0.00 volts versus copper sulfate. Option B, negative 0.50 volts. Option C, negative 0.85 volts. Option D, negative 1.50 volts. The correct answer is option C, negative 0.85 volts versus copper sulfate. At this potential, the steel is polarized into the immunity region. 0 volts provides no protection. Negative 0.5 is insufficient. Negative 1.5 is excessive and could cause hydrogen embrittlement or coating blistering. Problem 1. Faraday's law mass loss. A steel structure experiences a uniform corrosion current of 0.50 amperes. Calculate the mass of iron lost per year. Step 1. Write Faraday's law for mass loss due to corrosion current. Mass equals I times T times M divided by N times F. Step 2. Substitute the known values. I equals 0.5 amperes. T equals 3.154 times 10 to the 7 seconds per year. M of iron is 55.85 grams per mole. N equals 2. F equals 96,485 coulombs per mole. Step 3. Calculate the mass loss. The result is 4,557 grams, which is 4.56 kilograms. So 4.56 kilograms of iron is lost to corrosion per year. Problem 2. Sacrificial anode lifetime. A 25 kilogram magnesium anode is attached to a steel pipeline. The measured protection current is 0.85 amperes. How many years will the anode last? Assume 100% current efficiency. Step 1. Rearrange Faraday's law to solve for time. T equals m times n times F divided by I times m. Step 2. Substitute the values. M is 25,000 grams, N is 2, F is 96,485, I is 0.85 amperes, M is 24.31 grams per mole. Step 3. Calculate the time in seconds. It is 2.335 times 10 to the 8 seconds. Step 4. Convert seconds to years. Dividing by 3.154 times 10 to the 7 gives 7.4 years. So the magnesium anode lasts approximately 7.4 years. Problem 3. Galvanic couple prediction. A copper pipe is connected to a steel water heater in a plumbing system. Which metal corrodes? Step 1. Identify which metal is the anode. Iron at negative 0.44 volts is more negative than copper at positive 0.34 volts. Iron is the anode and will corrode. Step 2. Write the half reactions. Anode oxidation is iron to iron 2 plus 2 electrons. Cathode reduction is copper 2 plus 2 electrons to copper. Step 3. Calculate the standard cell potential. E cell equals positive 0.34 minus negative 0.44 equals positive 0.78 volts. This positive potential confirms the reaction is spontaneous. Steel corrodes and copper is protected. Problem 4. Corrosion rate in millimeters per year. A steel plate corrodes with a current density of 5.0 times 10 to the negative 4 amperes per square centimeter. Calculate the corrosion penetration rate. Step 1. Write the corrosion penetration rate formula. Rate equals m times I car divided by n times F times rho times 3.154 times 10 to the 7. Step 2. Substitute the values. M is 55.85. I core is 5.0 times 10 to the negative 4. N is 2. F is 96,485. Rho is 7.87. Step 3. Calculate the result. Rate equals 5.79 millimeter per year. So the steel plate corrodes at 5.79 millimeter per year. Problem 5. ICCP system design. A buried steel pipeline has a surface area of 5,000 square meters exposed to soil. The required protection current density is 15 milliamperes per square meter. Calculate the total current required and the rectifier voltage if the circuit resistance is 2.5 ohms. Step 1. Calculate the total protection current. I equals J times A. 15 milliamperes per square meter times 5,000 square meters equals 75 amperes. Step 2. Calculate the rectifier voltage using Ohm's law. V equals I times R. 75 amperes times 2.5 ohms equals 187.5 volts. Step 3. Add 2 volts for anode back EMF from oxygen evolution. V rectifier equals 189.5 volts. The conclusion is we need a rectifier rated at approximately 190 volts and 75 amperes. Select a standard rectifier of 200 volts, 80 amperes with 20% spare capacity. Let us pull together everything we have covered. Corrosion is the spontaneous electrochemical degradation of metals, driven by the formation of anodic and cathodic sites on the metal surface. The corrosion rate is governed by thermodynamics through Pourbaix diagrams and the Nernst equation, and by kinetics through the Toffel equation and polarization. Passivation provides natural protection through thin oxide films. Cathodic protection, both sacrificial anode and impressed current, is the premier engineered defense. It supplies electrons to suppress the anodic reaction. Faraday's calculations allow us to predict mass loss, anode lifetime, and protection current requirements. Together, these principles keep our pipelines, ships, bridges, and platforms safe from the destructive force of